Hello, welcome back to part two of the lecture. Uh, Before I finish part one, actually, I lost the internet connection, and therefore, at the end of the last part, part one, uh, there may be some uh, unclear parts. So, therefore, I will start with the example 1.2, which I was explaining at the end of the previous video. So we were looking at this example 1.2, uh, where we are given a certain joint density function of x and y, where x is the amount proportion of cashews and y is the proportion of almonds in a randomly selected mixed nut can. X plus y has to be less than or equal to 1. It can be less than 1 because there are other types of nuts also. Or maybe only those two are there. In that case, x plus y will be equal to 1. So the first part is derive the marginal probability density functions of x and y. And I was explaining how to find out the marginal distribution of x. Before that, actually, I discussed how one would find out a suitable model like what we have here uh, for the joint probability density function. Right? So I explained that part should be clear in the previous video. Therefore, I'm not going to repeat that. And then we discussed what we mean by the marginal distribution function of a single random variable coming out of a bivariate distribution. I explained that using uh, a Shiny app, and I was explaining it how to get that using the usual method by integrating out the other variable. And I think that's where the internet was disconnected. Therefore, I will restart at that point to discuss how to find out the marginal distributions, and then we go to the part two. So the question is how to find out the marginal probability density function of x, right? So generally it says f of x equal to from integration from negative infinity to positive infinity, the joint density with respect to y. But of course, even though we write down from minus infinity, negative infinity to positive infinity in general, in practice, what you have to do is at a given x, we have to now give the limits for y, right? So, what are the limits for y? Because we are integrating with respect to y, what are the limits for y when x equal to simple x? So, that is the question. Right? So, in order to understand that, I think it's better to look at the support of the density function. Right. So it says the support has to be x greater than or equal to 0, y greater than or equal to 0, and x plus y less than or equal to 1. So accordingly, our complete support is this large triangle here. In the support, the joint density function is defined over this large triangle. So what I want to do is now is to find out the marginal distribution function at a given x. Right. So in order to explain this, let me draw something. So for example, suppose I want to find out the marginal distribution at some value x here, right? So what I have to do is I have to integrate the density function. Suppose this is a vertical line. I have to integrate the joint density function with respect to y from this point to this point. Right. So I have to integrate the joint density function fx y x y with respect to y, but the limit now, if the value of x is somewhere here in that case y is start at 0, and then this value, this is the line x plus y equal to 1 line. So therefore here y is equal to 1 minus x at this point, right? This value will be 1 minus x. So therefore I have to integrate this thing from 0 to 1 minus x to get the marginal density function of capital X at x. Right? So that's what you have to do. Right. So it's easy to find out the limits of integration if you draw the support like this first. Right. So based on the given information, we can draw the support like this. Then we can do this. Right. Uh, so similarly, if you want to find out the marginal distribution of capital Y at some point, simple y, for example, in that case, you have to integrate the joint density alone this line. For example, suppose this is y, some value y here, right? And then we have to integrate the joint density function alone this line with respect to x, right? So therefore, x equal to 0 here, and x in this case, x is equal to 1 minus y. So in order to find out the marginal density function of capital Y evaluated at this particular value y, you have to integrate the joint density function of x and y with respect to x, and the limit of x should be from 0 to 1 minus y. Right? So you can see that then the whole thing is going to be a function of y, because you are integrating with respect to x and putting limits in terms of y. So finally the answer will be in terms of y. Marginal density function of x and y separately. So that's why I have calculated like this. Take any x, this in order to find out the marginal density function of x. This simple x that we are considering can be anything between 0 and 1. Uh, so this is what you have to do, right? Integrating with respect to y, but limits of integration is from 0 to 1 minus x, right? So then this is the calculation. And when you are integrating with respect to y, this 24 times x can be considered as a constant. You can take it out. So you have to integrate this y only. So therefore, y square over 2, and then limits has to be from 0 to 1 minus x. Finally, this is the answer you get. Right, so therefore, the marginal density function of capital X evaluated at simple x is given by this expression, and x, this simple x, can be anything between 0 and right. So therefore, we can write down more completely. Right here, I have written down this thing only. This actually implies that if x simple x is outside this region, then automatically this has to be 0. But if you want to explain, write down that also explicitly, you can write down it like this. Right? When x is between 0 and 1, it's given by this expression. Otherwise, the density is 0. And similarly, you can get the density function of y, as I mentioned, by integrating. In that case, this will be f capital Y within evaluated at some simple y. You are integrating this with respect to x, but the limit will be then 0 to 1 minus y. Right. So by symmetry, you can see that you will see that you can get the expression even by looking at this thing without doing the integration again. Fy will be then 12 times y, 1 minus y square, where that simple y is going to be between 0 and 1. So that I have not shown you the answer. You can obtain it by just looking at the symmetry of this density function. Right. Then we will go to part 2, where we have to find out the probability that x plus y less than or equal to 0.5. So, according to theory, now you are finding this thing, probability that x, in other words, generally what you are looking at here is something like this, right? So, you are looking at the probability that x, y point is in some set A, right? Satisfying this condition, right? So if you are finding this kind of expression, how you do is you integrate over A, right? F x y dx dy. You have to integrate the joint density over this A. It will be a double integration of with respect to x and y, satisfying this condition, right? So how do you find out that A here, right? You have to find out, first of all, figure out that area A or the set A, it will be a subset of the two-dimensional plane. And then you have to do the integration to cover that area. Right. So here what I want is x plus y less than or equal to 0.5. So if you mathematically, if you just consider the mathematical equation, we are looking at x plus y less than or equal to 0.5. In other words, y less than or equal to 0.5 minus x. Right. So we will consider this y is equal to zero point 0.5 minus x first and then find out the corresponding region satisfying this. So if you do that, uh, you will see that the area that you are considering is this area, the area in the blue color here. So this is the area that x plus y less than or equal to 0.5. Right. Now what you have to do is you have to integrate the whole joint probability density function, which is over the whole area, but now you are integrating over this area only, right? So how do you do that? We can do that like this. For example, first of all, you will integrate the uh, uh, the joint density function over a small stripe. For example, okay, let me consider a small stripe here. My drawing might not be vertical here. I'm going to consider a vertical stripe here at some x. Suppose the width of this thing is something like dx, right? So first I will find out the volume uh, under the joint density function, right? So in order to find out that one, I have to integrate the joint density function with respect to y, because y is the one changing here, x is fixed. So I have to integrate my joint density function with respect to y from here to here. Here y is equal to 0. Here y is equal to 0.5 minus x. Right? When this value is x here, y is equal to 0 at this point, y equal to 0.5 minus x at this point. So I'll have to integrate first the joint density from with respect to y from 0 to zero point 0.5 minus x. Then to get the whole integration over whole this region, then I'll have to move my x from 0 to zero point 0.5. This value is 0.5 here, right? So then the second integration will go with respect to x from 0 to zero point 0.5. So therefore, the probability that x plus y less than or equal to zero point 0.5 can be obtained by integrating with respect to y, f x y joint density with respect to y first dy, but y goes from 0 to 0 0.5 minus x, and then that I have to integrate with respect to x. Now x will go from 0 to 0.5. Right. So that's how you will get that area. Right. That is one way, one method. Or you could consider a horizontal stripe, right? So first you will consider a horizontal stripe like this. Right. So in that case, y value is fixed. Okay, so here I'm going to find out the volume under this small stripe. Now this is going to be dy, length is dy. Uh, but I'm considering the area under this, right? So change y is fixed, x is changing. X is changing from 0 to, at this point, x is equal to zero point 0.5 minus y, right? Because y value is here, y. At this point, x is equal to zero point 0.5 minus y. So in that case, I will be integrating first with respect to, integrating the joint density first with respect to x from 0 to zero point 0.5 minus y. And then I will differentiate with respect to y, right? From here to this point to this point to that point, right? So from 0 to zero point 0.5 here, right? 0 to zero point 0.5. So that's another way to get the same mask. So you can consider a vertical stripe here, and then integrate with respect to y along this that vertical line, or you consider a horizontal line and integrate first with along that line with respect to x, and then integrate later with respect to y. Right? Both ways, both methods can be applied. Uh, So remember, you are actually integrating some surface that is existing above this rectangle, and this rectangle, this last part, you are integrating the the volume spanned on this rectangle, the total volume. That is the probability that x plus y less than or equal to 0.5. So so this is how you do it. Integrate with respect to y from 0 to zero point 0.5 minus x first, and then integrate from with respect to x from 0 to zero point 0.5. Right. So you will get this answer. Right. So first do this part. Considering x, 24x as a constant, integrate with respect to y. And then when you put the limits in terms of x, everything will be now in x. There will be no y anymore. And then you integrate that quantity with respect to x and put the limits for x from 0 to zero point 0.5. So this is the whole calculation here. Then when you do that, you will get this answer 1 over 16 as the probability. That's how you get the probability uh, from a joint probability density function, right? In general, this is the method, right? So, of course, from problem to problem, the limits will be different, right? So, you better first of all draw a sketch of the support of the joint density function, uh, and then also draw whatever the subset that you are interested in. If you're finding the probability of some event in terms of x and y, you can identify that as a subset in your support. Right. So then you have to get the iteration to cover all the points, so that you will be finding the volume under the joint distribution, joint probability density function spanned on that particular set A, for example. Right. So that is the end of that problem. So that I couldn't complete that in the previous video because of the uh, internet disconnection. Right. So we will look at another example again, for a continuous case. So I hope I will be able to now completely consider this problem. A bank operates both a drive up and walk up window. Right. So that means some people uh, get their service from the car itself, drive up. Some people come up and inside the bank and then line up and get the service. A bank operates both a drive up and a walk up window. On a randomly selected day, let capital X denote the proportion of time that the drive up window is in use. So again, we're looking at proportion. At least one customer being served or waiting to be served. That's what we mean by in use. So X denote the proportion of time that the drive up window is in use per day. Actually, we are considering a day, right? This X is measured in hours. It's not clearly mentioned in the problem. This is again not coming from the Dominion course book. I have taken this one from some other book. Right. Uh, so what you get at is actually you can look at the total time that the drive up window and the up window was in use, and then out of that time, what is the time the drive up window was being used, and thereby you can get the proportion. Let y denote the proportion of time that the walk-up window is in use. Suppose that the joint probability density function of x and y is given by this mathematical expression. Right. So suppose, so you can think again how they got this particular joint density function, right? So one way to get this is by collecting a large enough data set on large number of days, right? They can find out x and y, and thereby look at the possible combinations and then find out uh, the proportions, how many times out of the total number of days that particular combination occurred, and thereby find out proportions, and then plotting or maybe using some kind of regression method, they can get an approximate expression like this. I think using, for example, uh, if they regress the proportion of time with respect to against x and y, considering x and y as uh, variables, they might be able to get this kind of expression, right, approximately. Right. So somehow they have got this thing, and they have not explained how they got it, but that's one method. It's possible. Right. So find the marginal probability density function of x, find the marginal probability density function of y, and find the probability that neither facility is busy more than 1/4 of the time. Right. That means find the probability means out of large number of days, what proportion of days where there neither facility was busy more than 1/4 of the time. Right. Okay, so in order to find out the marginal probability density functions, it's again better to look at the support of this function. Support is given by this x and y are actually independently changing here. There is no restriction related to x and y combinations like in the previous situation, x plus y less than or equal to 1. Right? So here x can be going from 0 to 1. Y also can be going from 0 to 1. There is no restriction in terms of x as a function of x and y. Right. So therefore, the support here is actually a complete rectangle, uh, x from 0 to 1 and y from 0 to 1. So I have looked at actually to just understand what we mean by this proportion of time walk-up window was in use and so on. So if the bank is open for T minutes, I think it seems that the problem is in minutes. Is it mentioned? Not mentioned here. So I'm assuming, I think, yes. Yeah. So if the bank is open for T minutes during the day and the drive up window was in use for D minutes, then X will be divided by T, right? T woke up window was in use as somebody. That means some people were getting service. Uh, D minutes out of the total T minutes, then the X will be equal D over T, and similarly if the walk up window was open for W, the previous one was drive up window. Right, walk up window was open for W minutes, then the Y will be W divided by T. Right, so that's what you have to observe if you want to get some idea about the uh, suitable density function. Right. So anyway, if I draw the surface joint density function given by this equation here, this equation, this is what I get. right? So x can be from 0 to 1, y can be from 0 to 1. So this whole thing, the surface is actually over the whole rectangle, right? So you can see that it is a surface, and here it's linear in terms of x, but it's quadratic in terms of y. So that's why there is some kind of curve going up here, right? What I have drawn here is actually the marginal distribution function, marginal densities. We will derive the equations for these things in order to just show that what we get as the marginal. I have drawn them. We will compare these and the equations that we get later. Right. So the question is how to get the marginal density function of x and marginal density function of y. Right. So in this case, it's very easy. In order to get the marginal density function of x, we have to integrate the joint density with respect to y. Right. So if you consider a particular x value, right, say for example, at this value of x, I want to find out the marginal. So I have to integrate the joint density function over this whole line here, right? So I'm sorry, I couldn't draw the straight line, but uh, y will be changing from 0 to 1. So I have to integrate the joint density with respect to y from 0 to 1 to get the marginal density at a particular x. And similarly, in order to get a marginal density function of y at a particular y, I have to integrate with respect to x. X will be changing from 0 to 1 again. Uh, so x will be changing from 0 to 1. So therefore, it's easy in this case. We don't have to, like in the previous case, 1 minus y or 1 minus x doesn't count because there's no restriction like in the previous situation, right? So therefore, the marginal density function of x evaluated at x is equal to the integration of the joint density with respect to y, but y goes from 0 to 1. And this is what you get in that case. So the marginal density function, you can see that it is a straight line, right? It's a linear function, straight line. X goes from 0 to 1. And you can see in the graph actually, it's a straight line here. So this is that marginal density function of x obtained by integrating the joint density with respect to y. And similarly, in order to get the marginal density of y at y, simple y, you have to again integrate the joint density with respect to x, but now x goes from 0 to 1, right? So therefore, the final answer you get, you can see that's a quadratic function of y, but y changes from 0 to 1. So this is a quadratic function. And if you go back and look at see, you can see that this is a quadratic function going with a certain curve. It's not a straight line. So that is that equation. So I want to find out the probability also. What is find the probability that neither facility is busy more than 1/4 of the time. So that means what is the probability that both x and y are less than 0.25, right? Quarter of the time. Right? So what is the probability that x less than or equal to 1 over 4 and y less than or equal to 1 over 4? So in that case, I'm looking at the probability in this particular rectangle, small rectangle. Right? Here 1 over 4, 1 over 4. So in this case, again, very easy to find out the volume under this one. What you have to do is you have to integrate if you want to integrate with respect to, suppose, for example, you are considering a vertical stripe. So you can first integrate, take a fixed x value with a small dx width stripe. you find out the volume under the joint density function over this stripe first of all. For that, you have to integrate with respect to y. Y changes from 0 to 0.25. Right. So integration of the joint density fx y x y dy, where y goes from 0 to 0.25. And then, in order to cover the whole rectangle, you have to change x from 0 to 0.25, right? So here x equal to 0, here x equal to 0.25. So you first find this part and then integrate with respect to x. X goes from 0 to 0.25. So that is the probability that x less than or equal to 0.25 and y less than or equal to 0.25. So that is that probability. So this is what you do. You have to integrate the joint density with respect to y from 0 to 104 and then with respect to x from 0 to 104. So when you are integrating with respect to y, when you are integrating this part, doing the simplifying, that part, this x will be considered as a constant, right? So therefore, when you are integrating, you are getting, you can take this 6 over 5 out, and then you get x times y, and then y cubed divided by 3, and then put the limits for y. Put the limits for y, not for x, right? Put the limits for y, and then you get this expression. Now it's going to be a function of x only. So integrate with respect to x and put the limits, and then when you get this answer. So that's another example. And then I'm going to show you a very useful model called bivariate normal distribution. Similar to univariate normal distribution, bivariate and multivariate normal distributions are very, very useful models in multivariate setting. You are using bivariate or trivariate or even more than three variables, then usually called multivariate normal. Bivariate normal sometimes called trivariate normal, and then usually multivariate normal with 4 dimension, 5 dimension, and so on. Right. So here I have written down a particular bivariate normal distribution with mean. When you talk about bivariate normal distribution, usually we have to mention the mean of, say, like suppose the random variables are x and y, then we have to specify the mean of x and standard deviation or the variance of x and mean of y and the standard deviation or variance of y. And then you have to, in addition to that, you have to specify the correlation between x and y. So there are 5 parameters involved. But here I have taken some particular values for mu, mean of x and standard deviation of x and mean of y and standard deviation of y. I have kept the correlation as a parameter because I want to show how the joint density, joint bivariate normal density function shape of that changes when other parameters are kept fixed, how the shape changes with the value of the correlation coefficient, right? Correlation coefficient is denoted by rho here, right? So what I'm considering here is a joint bivariate normal distribution with mean of x equal to 50, standard deviation of x equal to 5, mean of y is equal to 75, and standard deviation of y is equal to 10. And I have left rho as a parameter. So if rho is equal to 0, then actually in that case, bivariate normal distribution is just the product of two individual normal distributions when rho is equal to 0. But otherwise, we cannot get by just multiplying two density functions. So in that case, this is the density function, right? So you can see that if rho is equal to 0, here you just get 1, and rho, this part will be disappearing. So you'll have only 1 over. Notice that here in a univariate normal distribution, you have here root 2 pi and then sigma x, sigma y in the two distributions. So when rho is equal to 0, this is like root 2 pi times the 1 over 5 times this part, exponential this part, 1 over 2, this part will be again 1, right? And then times 1 over 10 square root 2 5 times 10 and then exponential minus half this part. So that's just the product of two individual normal distributions, one with mean 50 and standard deviation 5, the other one with mean 75 and standard deviation 10. That's what you get when rho is equal to 0. But otherwise, when rho is some other value, rho can be negative or positive in this case. I have considered a positive rho situation just to show you the distribution. So you can see that when rho is equal to 0, uh, the shape, in this case, the shape of the density function, joint density function is like that. By these red curves, I have shown the contours. Right, contours are the lines where the density is equal. The height of the density is equal. So you can see that it's in that case, it's symmetric around this mean 50 here and symmetric around the mean 75 here. I have chosen 75 and 50 as the mean of x and mean of y. So this is a symmetric cone, right? Symmetric around 50 and symmetric around 75 on this axis. But of course, the standard deviations will be different. But now you can see when rho is equal to zero point 0.7, it's not a complete cone, a usual cone. It's like pressed cone, right? It's like pressed, and then alone x equal to y line, it's going to be somewhat closer than this cone here. It's like a cone which is pressed alone x equal to y line, right? So you can see that the contours are not circles like this. Contours are ellipses in this case. So that's all I am going to tell you about the bivariate normal distribution at this point, because later on we will be using this distribution a lot of times. We will be finding out the marginal, conditionals, and so on later on. But I'm not going to do that here at this point because the mathematics is a little bit cumbersome than the previous situations, the integrations and so on. So therefore, I will just leave it like that. Right. So that is the end of one part, right? In that part, we discussed joint. In the previous video, we started with the joint cumulative distribution function and then marginal cumulative distribution functions and then joint probability mass function and the marginal uh, probability mass function and then joint probability density function and the marginal probability density functions. Now we will go further by discussing the properties, characteristics of these distributions. Usually when we talk about a distribution, there are several interesting characteristics like expected value, variance, and some other quantiles and so on, right? Median and that kind of things. The same applies here also. We are generally interested in the expected value of some function of x and y. And also we are interested in variance between variance of some function and also interested in finding out the covariance between x and y and so finding out the variance of some function of x and y. So here, therefore, we define first of all, the expected value of some function of x and y. Suppose the function is g. So expected value of g of x and y. So x and y are both random variables. Therefore, g of xy is also a random variable. So these again, if you go back and look at your notes, you will see that this is a direct extension of the univariate case. In the univariate case, if you're considering expected value of g of x, in that case, you have only single summation g of x times the probability mass function of x. That product has to be added. over all possible x's. Now you are doing the same thing, but now you are adding over x and y, all possible x and y. In this discrete case, you will be adding over all possible combinations of x and y. G of xy times the joint probability mass function. And similarly, taking the corresponding term for the continuous case, expected value of g of xy will be the double integration of g of xy times the joint density with respect to x and y, right? So theoretically, we say again from minus infinity to plus infinity, but of course, the practical situation, we'll require to integrate this only over the support of this joint density, right? Outside the support, of course, the joint density part will be zero, and therefore integration coming from that part will be zero. So therefore, it is enough to integrate over the support of uh, the joint density in a special case, right? So this is in general.